Hi there. Today we're looking at the Imputer sequence modeling via imputation and dynamic programming by William Chan, Chitwan Saharia, Jeffrey Hinton, Mohammad Nuruzi, and Navdeep Jaitli. So this is a model to perform sequence-to-sequence tasks. Now, sequence-to-sequence tasks are very, very common in NLP, but in this case, it's kind of a subset of sequence-to-sequence tasks. So a classic sequence-to-sequence task is machine translation. Here, for example, the sentence, I like you. If you want to translate it to German, you. If you want to translate it to German, that would become Ich mag dich. And you see that the input is a sequence, right? And the output is a sequence. Now, the imputer deals with very special kind of sequence-to-sequence tasks. Namely, it deals with sequence-to-sequence tasks where there is a monotonic alignment. So you see that this is given here. The first word is corresponding to the first word here, the second to the second, and the third to the third. This is not always the case in machine translation. You know, different languages have different sentence structures. So, for example, in French, this would be je t'aime. And you can see that the first word is still the first word. However, the third word has become the second, the you, and the verb goes to the end. So the imputer would not be able to deal with this task very well. A different task where the imputer would be useful for would be something like speech recognition. So if someone were to speak the words I like you, and you would measure the waveform of that, it would look something like I like you. Right? So if you have this waveform, let's actually make some chunk samples out of this. Let's say this is a sample right here, and here is a break, here and here, right? So we have 5 samples on the bottom, right? And you can see pretty easily that this sample here, this is the I, then this is silence, this is the like, this is silence, and this is the you. So the imputer deals with these kind of sequence-to-sequence tasks where, first of all, there is a monotonic alignment, and second of all, this is an engineering constraint where the length of the input sequence X is larger or equal to the length of the input sequence Y. And you'll see why, mainly because we rely on being able to compute this alignment here. The alignment of input samples to output samples, right? You can see that the monotonic alignment is actually given fairly well in speech recognition, because if something is later down here, it is also later in the sequence up here. That is a monotonic alignment. And also, usually, we have more wave samples than we have words in the output sequence. So that would be a task for the imputer. Now, let's think about how we would do something like this. So let's put X at the top here. And we said X has 5 tokens in it. And let's put Y at the bottom, right? Y actually has 3 tokens, right? So this here is I like you. This is the waveform, right? And we want the I like you at the bottom. So what could we do? Right. First of all, what the imputer does is it represents I like you not as this form right here, but as a form where you have the same length as X divided into the same amount of things, and then it does the following. So for this is an example. Right. This is how it would represent Y, right? It would say, I have as many chunks on the top as on the bottom. I know this chunk here corresponds to this token. Then this here to this, and this here to this. and then these are these intermediate ones, right? So you can see these correspond to those. These are silence right here. Now, it doesn't always need to be that there is always one token, then a silence, then a token, then a silence. The task of the imputer is actually to see whether this is more likely than, for example, I like, and then silence, silence, and then you, right? So the task of the imputer is to distinguish these two from each other, and then, of course, also produce the actual tokens. Now, if you think about how would you go about taking X and producing something like Y. So this is Y, let's call it tilde. This is the actual Y, right? But you can see that this here is a deterministic function in one way. It's actually not a deterministic function in the other way. And that becomes interesting when you have to compute a loss for this. But how would we go about doing this, right? What we could do is we could just take a big transformer, BERT, right? Let's actually draw an arrow. We could just take BERT. And we could simply, so in BERT, you have, if you construct it correctly, you have as many input tokens as output tokens. So what we could simply say is for each of the outputs that we get, we simply make this as a softmax classifier over our vocabulary, with the silence being one special token, and we simply classify each of the outputs into this vocabulary. This would be one step, right? So we could do one step BERT, bang bang, input to output. And there is more, there are more sophisticated approaches to doing this in one step, like CTC, but ultimately we could just do one step. But then you'd have the same problem like, for example, XLNet. If you haven't seen my XLNet video, I recommend it. They exactly take the problem. If you do this, right, then at the moment where you decode the word like, you have no idea that there is an I over here. All you know is the vector you have here that you sample the I from, right? But this could be a distribution where I is pretty high, but some other word is also pretty high. So this process over here that samples the word like has no idea which of the two here you actually would sample. So it cannot condition on it. So it is the assumption here is that the sampling of the word like is independent of the sampling of the word I. And of course that's not the case. You need to know what word is there if you want to sample the word like. Otherwise you can end up with some very confusing sentences. So this one-step process is pretty quick, but it has the drawback that there are these conditional independence assumptions. And again, I invite you to watch the XLNet video if you want to dive more into this problem. The second thing we could do is we could just decode one after another, right? So we could say, all right, I'll make my 5 slots here, and I just leave them empty for now, and I'm just going to decode the one that I am most sure about. And let's say the speech at the back here is very clear, and you say, I know this is a U, right? So I'm going to fill in U right here, right, and make this alignment. So this goes here. This is the U, right? I still don't know what the others are, but now what I do a second step. And in this second step, I get as an input not only the original input, like this thing here, but I also get the fact that I already decoded the word U to here, right, in this step. So now I say, given that I already decoded the word U, which one am I now most sure about? And might be most sure about just say, I'm most sure about this now being an I, because there's a U at the end, and this kind of sounds like an I, so an I here, right? It goes to the next step. And in the next step, it already has the information that it decoded I and U. And now it might say, okay, given these, so probably this thing, so I here, probably the thing here The thing right here is silence, right? Makes the most sense. I kind of hear some noise, but there's already a word after. So now I'm pretty sure that this here is a silent token, right? And you go this until the end, until you're actually at this. So this here would be n-step decoding. This here would be n steps of decoding, which now no longer has the problem of these conditional independence assumptions, but of course, now you have the problem that you need n steps, right? The imputer does something in the middle of this. The imputer will, as you can see here, it will form this into blocks, right? Blocks of size b. And this is the empty symbol here, right? And what it will do is it will make a step where in each block, for each block, it will, conditioned on the previous alignment and conditioned on the input, it will decode whatever it feels it is most certain about in each block. And then it does this for as long as there are still empty tokens, right? You can see here the first block, and then in the second step, it will decode this, 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 and this. So the imputer can trade off between the conditional independence assumption of the one-step BERT and the full conditional dependence assumption of the n-step decoding. Right, so it will compute this alignment and the actual tokens at the same time in this process. So how many steps does this take? This takes now b steps. And this is pretty cool because b is the block size. So this is independent of the sequence length. So it is able to compute this alignment and output in a constant number of steps, right? So you're, by modulating this b, you're now able to trade off speed versus, let's say, performance in the imputer. And this is pretty cool. So I think the bigger point to understand here is how to actually use the assumption that there is a monotonic alignment, right? Because if there is a monotonic alignment and if this thing is given here, then you can do this representation right here with the silence tokens, and that allows you to basically represent the output in a form that is of the same length as the input and do this kind of token by token decoding while still allowing you to have variable lengths output as long as they're smaller in length than the input. So that's pretty cool. And then the next pretty cool thing is the fact that they do this in blocks. Now, of course, my issue with this, so this is how the system works. My issue with this is how the system is trained. So if you think about how you train this, you must train this. First of all, the loss function, right, has to revert this. And how they do it is they marginalize, you see this down here, you want to marginalize over all the possible alignments right here. And so this is how you train. You sample an alignment from the alignment policy. And this alignment policy is... I think they have some heuristics of how they construct the alignments during training, or you have experts actually giving you this alignment. I think they use, in the speech recognition, they use something like CTC to give you the alignments from the alignment policy. And then you have a masking policy. And I think they just do random masking, and then they use that for training, and then they marginalize over the alignments. This, I'm pretty sure, is not the same distribution as the decoding procedure I just described. Right, so the decoding procedure, if you do this in B steps, right, that means each of the step is dependent on the step before. So that means the distribution of whatever the imputer sees is actually dependent on itself. While these people are proposing a training framework where you have here you have a heuristic in order to come up with the training sample alignments, and here you have a random, I think a random masking policy that comes up with where the empty tokens are. So this is not the same distribution, and then also it marginalizes over all compatible alignments, which I'm pretty sure this is not the same distribution. This is not the correct loss distribution. They have some math to show that in expectation it's the same, but yeah, this is over their roll-in policy and and marginalization. This I don't want to go too deep into this. I've given it some thought, but it will make this video too long and boring if I actually go into the details here. Suffice to say, I invite you to look at the loss computation and ask yourself if you think that is the correct way to produce the data set for training, given how you do the inference later. The architecture of the imputer is actually pretty similar to BERT in that, first of all, well, okay, you're dealing with audio in the input, so you're going to have some convolutional network here, and you also need to take as an input the prior alignment that you've already produced, right? So this you embed, but then you simply do an attention network, a transformer, which is pretty close to the BERT example we've made. And so, I mean, they stress that their loss is actually a lower bound on the loss. So I shouldn't be too hard when I say it's not the correct distribution. They do minimize something, some loss that actually makes sense. But yeah, I mainly wanted to go over how the imputer works and how it is structured, and I think it's pretty cool, and it lends itself very well to these tasks. And most of all, I like the fact that it exploits these assumptions here. So not all tasks fit these assumptions, but if a task does fit the assumption, then I think it should be, it should be fairly obvious that one should exploit that in order to perform better. All right, that was it from me. Thanks.